Okay, the video then on audio. So you need to know maximum power transfer, maximum voltage transfer. So maximum power transfer, we're looking for both V and I to be as big as possible, and that usually occurs when for the power amplifier to the loudspeaker. So we're obviously looking at Y to Z. Whereas otherwise, if we're looking at maximum voltage transfer, that would be all of these other subsystems where we're looking for the input resistance of the next subsystem to be a lot bigger than the output resistance of the previous subsystem, which obviously leads us to the next one. So relationship to R1 maximum power transfer, well, we want them to, in this case, to be equal. Okay. So we've got a preamplifier here. We've got a preamplifier. It's made from a non-inverting amplifier. So gain for a non-inverting amplifier 1 plus RF over R1. So we've got 1 plus 750 over 30 equals 26. So we've got a gain of 26. Therefore, then, if the overall voltage gain, that answers what the overall. What is the overall voltage gains of the preamplifier? That's what that is. I'll just come on to another thing in a minute. But we've got then bandwidth equals gain bandwidth product divided by gain. So therefore we've got 3 times 10 to the 6 divided by 26 gives us a bandwidth of 115.4 kilohertz. So if this one had, if they were both if these were both amplifiers here of gains of 26, then the overall gain that we've got there is going to be 26 times 26. So obviously just putting that in as an extra little cookie. Capacitors then, the capacitors there are for decoupling, so we can block DC. So the block DC. And then we're looking to draw. What are we looking to draw? So we're looking to do a boost, and we're looking to do a boost and for below 200 kilohertz. So we've got a voltage gain of 2. So I'm now going to identify 2. So if that is 1, then this one must be 2. So and then this is my 200. So I'm going to draw a nice flat line in there like so, and that is my break frequency. And then I'm going to draw a 45-degree line going up. Well, obviously I can also put an extra point in, but that's 200 hertz. I can go down by a factor of 10 to 20, and then if that was 2, then I can go up to 20 kilohertz, 20 hertz, sorry, as well, and that will obviously aid me in drawing my line at 45 degrees. So 45 degrees, like so. Right. Okay. I debated obviously changing this question here because it's drawing a filter and like so, and so we're going to have a 39k resistor just there. We're going to have our 82k resistor here, and you can obviously work them out yourself. That gives us a gain of minus 2.1, and the capacitor is there because I'm wanting to do a bass boost, and then that goes down to, where's the 0 volts gone? There it is, down to the 0 volts like so. So I'm not going to put in the values in there. You can do them, but certainly have a look at this question, because you could certainly be just given say that it's got to have an input resistance of 39k, and then you've got to then work out what these other two values. That's more of a realistic question, I've got to say. Okay. But that's the circuit that we've drawn, and obviously don't forget to put your blobs in. Moving on forward, then we've got a graph to interpret. Well, two-line approximation. We've got a break frequency there of 5 kilohertz and a gain of 5. Okay, so we've got 20 there. So 20k times by 5 equals 100k. So therefore RF is going to be 100k. Okay, this is just a treble cut filter or a low pass, depending on how you want to call it. Okay, which means for me, for a treble cut filter, the capacitor is going to go on top like so, 100k like there. So I've got my value of C that I've got to go and find. Well, we know that our break frequency equals 1 over 2 pi RC, but we'll obviously want to swap it around, so C is going to be then equal to 1 over 2 pi times by the 5 kilohertz break frequency multiplied by the resistor associated with the capacitor, so that's my RF, so 100k gives me 318 picofarads as C. Right, that was straightforward. Right, I've modified this question here. So what is it this question is asking here? Is, well, minimum input of 10k, but it's effectively saying, well, okay, I want a circuit that's going to take 2 voltage input. The first one has got a gain of 4, and then the second one has a gain of 1. So we get that's what we could have as an equation. Channel 1 has the most gain, so that is going to be the resistor value that I start off with, because that's going to be the one that is the minimum value of resistance. Oh, sorry, I got a bit carried away. This circuit here wants us to put some variable resistors in so we can adjust what we've got. So let me just do that like so. So there's R1, there's R2, there's RF, like so. Okay, so yeah, so channel 1 has got the resistance. So if we let R1 equal 1k and it's got a gain of 4, so RF is going to be 4 times 1k, which equals 4k. And as channel 2 has a gain of 1, therefore R2 equals RF, which equals 4k. Okay, Scooby-Doo. Right, okay, so we just go then slot the values in. So we've got 10 millivolts going in on one of them, and the first channel has a gain, and it has a gain of -4. The second channel has -4 millivolts going in, but it has a gain of -1. So doing that in turn, we've got -40 millivolts plus 4 volts times a minus equals a plus. 4 millivolts equals -36 millivolts as our summation. Right, okay, so we're on to a biased emitter follower now. Yeah, a biased emitter follower. So we're going to have, so what's the voltage there? 2 equal sized resistors, so it's just going to split the voltage. Just here at 3 volts, we've got the difference between there and there, so it's going to be -0.7 equals 2.3 volts. No power, so I don't often use this equation, but it saves me calculating the current. So power V squared divided by R, so we've got 2.3 volts squared divided by our 8 ohm speaker gives us 661.25 milliwatts. Right, okay, so plotting this on the graph. So this is the signal that we've got at X. So the first thing that we've got, and I'm going to pause the video in a minute, is that our signal at just here is superimposed on the 3 volts. So 4, 8, 12. So there is my 3 volts. So I'm going to put a dotted line in like so. Okay, that's going to go across there. Then, so if that's 3 volts, my maximum signal is there, and I've got 2 volts. So 2 volts, but then my signal is going to go from this 3 volt point up by 2 volts. But then I've got to take into account the transistor, so minus 0.7. So my maximum will be at 4.3. The lower line, if starting off at 3, it's going down here to minus 2. So minus 2, and then taking off the 0.7 gives me 0.3. So when I've got a maximum here, I'm scanning up to 4.3 volts, which is somewhere there, and then coming down here to minus 3. Okay, and then the only other things that I've got to do then is my signal has got to get above 0.7 of a volt, so it's going to be approximately here that happens. So I can put another cross in there, approximately there. I can put another cross in there, which then now allows me to draw my waveform. Okay, so drawing the first part of the waveform in looks like that. I'm not sure why I put that cross in there just like so, because there is my minimum point, so therefore then that's where I need to have my minimum point. This point here was going to be a cross there, so therefore I can then pop that in like so. Okay, it's lovely then. Right, okay, so to improve our circuit, then we can use a push-pull configuration. I thought this was different because it has MOSFETs, and we don't often get to draw a MOSFET. So first of all, I'm going to draw an N-channel MOSFET. So on an N-channel MOSFET, we need to put a arrow going in, like so, and there we have it going down to there. And then we need to draw our P-channel MOSFET. Now we're going to draw our P-channel MOSFET in a similar sort of fashion, but instead this time the arrow comes down. Okay, and then we just need to connect the two MOSFETs together. Okay, where does the speaker connect to? Well, it connects to the middle of the two MOSFETs, like so. We've already talked about what the job of the capacitor is, so I'm not going to write that down. Okay, so the problem we've got with one of these circuits is we suffer from crossover distortion. And as it's a MOSFET, and we're saying that V threshold is 3 volts, so at my maximum there, we're only going to get 7 volts out when maximum, which is going to be there. But it's not going to conduct until the voltage is above 3 volts. So at that point there, I'm putting a line in there like that, and I can then put it, and it'll come down to there. And same when we've got negative 3 volts, it's not going to conduct, which is there. So I'm going to put a dotted line in like so, and a dotted line in, keeping that going, dotted line in like so, because it allows me to draw all of my points. So what's going to happen is my my MOSFET won't conduct until I've got 3 volts in, and then it'll start to conduct, reaches its maximum, and then as soon as the signal then drops below 3 volts, it stops conducting, and then we end up with this crossover distortion. Didn't put a point in down there, well, silly me. So we end up with a signal that looks like that. So this bit is the crossover distortion, 3 volts. Okay, so just back to our one with transistors. So maximum power dissipated. So when we've got push-pull amplifier, we've got a special formula we can use, which is Vs squared divided by 8RL. Now Vs equals the difference between power rails, and if there's no no feedback, technically we need to take into account the crossover. So the top line there, we're going to have 12 and 12 is 24 volts minus the 1.4 that we've got for each of the transistors for the crossover distortion, squared divided by 8 times by 8. So I'm going to answer for this one. 24 minus 1.4, square that, divided by that, gives me a power, I believe, of 7.98 watts. What's the advantage of using this configuration? Advantage of the arrangement over emitter follower, which uses split bias. Well, with the emitter follower with split bias, it means that the transistor or MOSFET is always on. So there's going to be no power dissipated when no signal. Okay, I'm not sure if we've got a little bit of a lag going on, but hopefully the video will obviously manage it. Right, okay, so we want to make things better. So we're just going to adapt our push-pull configuration. So I'm just drawing in my my PNP transistor there, like so. What we need to do is connect up the bases of those two transistors. We then need to put in a voltage follower. So we got there, and where does that voltage follow? Well, it needs to follow the output. So our output is taken from the middle of the transistors, and then we can take our feedback needs to come back into the inverting terminal, which means the output then turns our two transistors off and on. We've already done a question like this. What is it? That is right, it's going to be 8 ohms. Okay. And we'll leave it there, I think.